Welcome to the Whispering Universes channel, where tonight we embark on perhaps the most profound journey of all, the possibility that you and every living thing you've ever encountered are ancient cosmic travelers. What if I told you that the very cells breathing life into your body right now carry within them the memory of distant stars? What if the story of life on Earth didn't begin in some warm little pond, as Darwin once imagined, but in the vast, cold depths of space itself? Tonight, we explore the Panspermia hypothesis, the revolutionary idea that life didn't originate on Earth at all, but arrived here as seeds from the cosmos, carried across the infinite darkness on cosmic winds, nestled within asteroids, or perhaps even deliberately planted by intelligences we can barely imagine. This isn't science fiction, but a serious scientific hypothesis that's gaining ground as we discover just how resilient life can be and how hostile our early Earth truly was. The word panspermia comes from the ancient Greek, meaning seeds everywhere, the idea that the universe is filled with the ingredients and origins of life, that what we call terrestrial biology is really cosmic biology, that we are not alone in our small corner of space, but part of a vast, interconnected web of life that spans the stars themselves. Consider this gentle possibility as your breathing slows and your mind opens to wonder. Every organism on Earth, from the bacteria in your gut to the great whales in our oceans, from the smallest virus to the most complex human brain, might all be descendants of ancient astronauts, not little green beings in flying saucers, but microscopic pioneers that survived journeys across the cosmos that would kill any complex creature in minutes. There are three main pathways life might have taken to reach our world. Lithopanspermia suggests life traveled as hitchhikers, within rocks blasted off other planets, surviving the cold journey through space, protected within their stone vessels. Radiopanspermia proposes that life itself, perhaps as hardy spores, could survive the radiation and vacuum of space over cosmic distances. And most intriguingly, directed panspermia suggests that advanced civilizations might have deliberately seeded worlds like ours with the building blocks of life. What once seemed like pure fantasy is now taken seriously by Nobel Prize winners, NASA researchers, and astrobiologists around the world. As we've discovered life thriving in Earth's most extreme environments, in boiling hot springs, in the crushing depths of ocean trenches, in the radioactive zones around nuclear reactors, even in the vacuum of space itself. The idea that life could survive an interplanetary or even interstellar journey seems not just possible, but probable. This changes everything we thought we knew about ourselves. If panspermia is correct, then looking up at the night sky isn't looking out at alien territory, it's looking home. The stars aren't distant and foreign, they're family. And the search for extraterrestrial life isn't a search for the alien, but a search for our cosmic cousins, perhaps even our cosmic ancestors. Let your mind drift across the cosmic ocean where life voyages between worlds, carrying the eternal flame of consciousness from star to star, world to world, in an endless dance of survival and renewal that makes the entire universe not just alive, but family. The idea that life might come from the stars is as old as human thought itself. Long before we had telescopes or spacecraft, before we knew what stars were or understood the vast distances between them, ancient minds looked up at the night sky and wondered if the lights above might be connected to the life below. In ancient Greece, around 500 BCE, the philosopher Anaxagoras proposed something that seemed radical, even by the standards of Greek cosmological thinking. He suggested that the seeds of life, what he called spermata, existed everywhere in the cosmos, waiting for the right conditions to take root and grow. To Anaxagoras, life wasn't a rare accident that happened once on Earth, but a cosmic principle that expressed itself wherever conditions allowed. This wasn't merely philosophical speculation. Anaxagoras had observed meteorites falling from the sky, and he reasoned that if rocks could travel from the heavens to Earth, why not the essence of life itself? His insight was remarkably prescient. Modern scientists have indeed found organic compounds in meteorites, and we now know that rocks regularly travel between planets, carrying whatever hardy organisms might survive the journey. The idea evolved through the centuries. Medieval Islamic astronomers, building on both Greek philosophy and their own careful observations, developed sophisticated theories about the plurality of worlds. Al-Qazwini in the 1200s wrote about countless worlds beyond our own, each potentially harboring its own forms of life. These weren't just philosophical exercises, but careful attempts to understand the cosmos based on the best available evidence. The Renaissance brought new urgency to these questions. Giordano Bruno, the Italian philosopher who was burned at the stake for his revolutionary ideas, proposed not just that there were infinite worlds, but that these infinite worlds teemed with infinite varieties of life. Bruno's vision of a universe filled with living worlds, where life moved freely between the stars, was too radical for his time, but it planted seeds that would later bloom into scientific hypotheses. The transformation from philosophy to science began in earnest during the 1870s, when the great physicist Lord Kelvin gave panspermia its first rigorous scientific formulation. Kelvin had been studying the cooling of the Earth and realized that our planet's early conditions were far too hostile for life to have originated here. The surface was molten rock, the atmosphere was poisonous, and meteor bombardment was constant and devastating. But Kelvin also knew that meteorites regularly fell to Earth, and he reasoned that if our planet could receive rocks from space, some of those rocks might carry passengers. We must regard it as probable in the highest degree, he wrote, that there are countless seed-bearing meteoric stones moving through space. This wasn't speculation, but careful scientific reasoning based on the best evidence available. The idea gained its most sophisticated early expression through the work of Svante Arrhenius, the Swedish chemist, who would later win the Nobel Prize for his work on electrolytic dissociation. In the early 1900s, Arrhenius developed what he called radiopanspermia, the theory that life could travel between worlds, not in rocks, but as hardy spores pushed through space by the radiation pressure of stars themselves. Arrhenius had calculated that bacterial spores could survive in the vacuum of space for thousands, perhaps millions of years. He showed that radiation pressure from stars could accelerate these microscopic travelers to enormous speeds, potentially carrying them between star systems in geologically reasonable timeframes. Most remarkably, he demonstrated that the same solar radiation that pushed the spores through space would also protect them from the harmful effects of cosmic rays. This wasn't just theoretical work. Arrhenius conducted actual experiments, subjecting bacterial spores to extreme cold, vacuum, and radiation to test their survival limits. He found that life was far more resilient than anyone had imagined. Spores could survive temperatures near absolute zero, complete vacuum, and radiation levels that would quickly kill complex organisms. The early 1900s saw panspermia evolve from speculative philosophy into testable scientific hypothesis. Researchers began to understand the mechanisms by which life might travel between worlds, the conditions it would need to survive the journey, and the environments it might encounter upon arrival. The shift was profound. Instead of asking whether life could travel between worlds, scientists began asking how it traveled and where it might have originated. By the mid-1900s, panspermia had gained enough scientific respectability that serious researchers were proposing specific mechanisms, making testable predictions, and designing experiments to explore its possibilities. The ancient dream of cosmic life had become modern scientific inquiry, opening new frontiers in our understanding of life's origins and distribution throughout the universe. What emerged was a new perspective on life itself, not as a rare accident confined to Earth, but as a cosmic phenomenon, a universal principle that expresses itself wherever conditions allow, connecting all living things in a vast web of biological relationships that spans the stars themselves. In the mid-1900s, as the scientific establishment was grappling with evidence for an expanding universe and what would later be called the Big Bang, one brilliant and controversial astronomer was developing a radically different vision of cosmic history, one that would breathe new life into the panspermia hypothesis. Fred Hoyle, the Yorkshire-born mathematician and astronomer, was never one to accept conventional wisdom without a fight. While most cosmologists were embracing the idea that the universe had a beginning and would have an end, Hoyle proposed something that seemed almost mystical in its implications: the steady-state theory, which suggested the universe had always existed and would always exist, continuously creating new matter and energy to maintain a constant density as it expanded. But Hoyle's most revolutionary insight wasn't about the universe's structure, it was about its contents. Working with his colleague Chandra Wickramasinghe, a brilliant astrophysicist from Sri Lanka, Hoyle began to explore what the cosmic environment might mean for the origin and distribution of life. What they discovered would challenge everything science thought it knew about biology. Their journey began with a puzzle about interstellar dust. Astronomers had long known that space between the stars wasn't empty. It contained tiny particles that absorbed and scattered starlight, creating the dark lanes visible in the Milky Way. But when Hoyle and Wickramasinghe analysed the spectral signatures of this dust, they found something unexpected. The absorption patterns matched those of organic compounds, the complex carbon-based molecules that form the foundation of life. This wasn't just a curious coincidence. The more they studied interstellar dust, the more convinced they became that space was filled with the building blocks of life: amino acids, sugars, even complex polymers that might serve as precursors to DNA and RNA. The vacuum of space, they realized, wasn't hostile to organic chemistry, but was actually a vast laboratory where the ingredients of life were constantly being synthesized and refined. But their most startling conclusion was yet to come. If space was filled with organic compounds, and if these compounds were constantly raining down on planetary surfaces throughout the galaxy, then perhaps life hadn't originated on any single world at all. Perhaps life was a cosmic phenomenon, as natural and widespread as gravity or electromagnetism, expressing itself wherever conditions allowed. Hoyle and Wickramasinghe proposed that comets were the primary delivery vehicles for cosmic life. These ancient wanderers, they suggested, weren't just chunks of ice and rock, but were actually repositories of living organisms, preserved in the deep freeze of space for millions or billions of years, waiting for the warmth of a nearby star to awaken them from their cosmic hibernation. Their theory explained many puzzling observations. Why did life appear on Earth so quickly after conditions became favorable? Because it didn't need to evolve from scratch. It was already fully formed, waiting to be delivered. Why did the same basic biochemistry appear everywhere on Earth? Because all terrestrial life descended from the same cosmic ancestors. Why did life seem to appear in sudden bursts throughout evolutionary history? Because new waves of cosmic immigrants were constantly arriving. The establishment's reaction was swift and harsh. Hoyle and Wickramasinghe's ideas were dismissed as speculation, fantasy, even pseudoscience. Their papers were rejected by major journals. Their conference presentations were met with skepticism bordering on hostility. The scientific community, which had just begun to accept the possibility of extraterrestrial life, wasn't ready to embrace the idea that such life might already be here. But Hoyle and Wickramasinghe persevered, accumulating evidence and refining their theories. They pointed to the organic compounds found in meteorites, the complex chemistry observed in interstellar space, and the remarkable speed with which life had colonized every available niche on Earth. They showed that the early Earth was far too hostile for life to have originated here naturally, while space itself provided ideal conditions for the preservation and transport of living organisms. Most provocatively, they suggested that evolution itself might be driven not just by random mutation and natural selection, but by the constant influx of genetic material from space. Viruses, they proposed, might be cosmic messengers, carrying genetic innovations between worlds and even between star systems, accelerating the pace of evolutionary change far beyond what Earthbound processes could achieve. Their ideas gained unexpected support from the 1980s onwards, as researchers began finding organic compounds in meteorites, detecting complex chemistry in interstellar clouds, and discovering that life could survive in space conditions that had previously been considered instantly lethal. The discovery of extremophiles, organisms that thrived in conditions resembling those found in space, lent credibility to their proposals. Perhaps most importantly, Hoyle and Wickramasinghe had shifted the conversation about life's origins from a terrestrial to a cosmic perspective. Instead of asking how life might have arisen in some warm little pond on ancient Earth, scientists began asking how life might move between worlds, how it might survive cosmic journeys, and what role the universe itself might play in biology. Their steady-state cosmology ultimately fell to mounting evidence for the Big Bang, but their insights about cosmic life proved more durable. Today, researchers routinely study organic compounds in meteorites, investigate the survival of organisms in space environments, and seriously consider the possibility that life moves freely between worlds. Hoyle and Wickramasinghe had transformed panspermia from a fringe hypothesis into a legitimate field of scientific inquiry. They showed that the universe isn't just a stage for life, but an active participant in life's drama, constantly creating, preserving, and distributing the ingredients and organisms that make biology a cosmic phenomenon. In 1973, one of the most respected scientists in the world published a paper that would shake the foundations of biology. Francis Crick, co-discoverer of the structure of DNA and Nobel Prize winner, proposed something that seemed to belong more in science fiction than in serious scientific journals: that life on Earth had been deliberately planted here by an advanced extraterrestrial civilization. Crick called his hypothesis directed panspermia, and he wasn't proposing it lightly. This was a man who had spent decades unraveling the deepest mysteries of life, who understood better than almost anyone how genetic information was stored, transmitted, and expressed. When someone of Crick's stature suggested that life might have extraterrestrial origins, the scientific world had to listen. His reasoning began with what he called the phosphorus problem. Life as we know it depends absolutely on phosphorus. It's an essential component of DNA, RNA, and the energy-carrying molecule ATP that powers every living cell. But phosphorus was extremely rare on the early Earth, so rare that it's difficult to explain how life could have originated here naturally. The early Earth simply didn't have enough of this crucial element in forms that primitive life could use. Crick noted that an advanced civilization, one capable of interstellar travel, would have had access to the entire periodic table. They could have selected planets with the right chemical composition, or even terraformed worlds to make them suitable for life. They could have solved the phosphorus problem, and many others, simply by choosing their targets carefully and perhaps even modifying the environments they seeded. But Crick's most compelling evidence came from the genetic code itself. DNA uses a universal language. The same basic code that translates genetic information into proteins in bacteria also works in plants, animals, and humans. This universality had always puzzled biologists. If life had originated independently in many different environments on early Earth, why didn't it evolve many different genetic codes? Why was there just one, used by every living thing? Directed panspermia offered an elegant explanation. If all terrestrial life descended from a single, founding population, deliberately introduced by cosmic gardeners, then of course, it would all share the same genetic code. The universality of DNA wasn't evidence of independent origin, but of common ancestry. Ancestry that traced back not to some primitive terrestrial organism, but to the sophisticated biological technology of an advanced civilization. Crick also pointed to what he called the Goldilocks problem of early Earth. For the first billion years after its formation, Earth was almost certainly too hot, too chaotic, and too hostile for life to survive, let alone originate. The surface was molten rock, the atmosphere was poisonous, and massive asteroid impacts regularly sterilized any potentially habitable environments. Yet somehow, life appeared almost as soon as conditions became even marginally tolerable. This timing seems suspicious to Crick. Evolution by natural selection is an inherently slow process, requiring millions of generations for complex systems to emerge. Yet life on Earth showed signs of sophistication from its very earliest appearances. The metabolic pathways, genetic mechanisms, and cellular structures found in the oldest fossils were already remarkably advanced, suggesting they had evolved elsewhere over much longer timescales. Working with Leslie Orgel, another distinguished biochemist, Crick developed the mathematical framework for directed panspermia. They showed that an advanced civilization, even one confined to a single star system, could seed hundreds or thousands of worlds over the course of millions of years. Automated spacecraft could carry carefully designed organisms to promising planets, releasing them when conditions were favorable. The organisms themselves would need to be hardy, capable of surviving the journey and establishing themselves in alien environments. But they wouldn't need to be complex. Simple bacteria, or even simpler self-replicating molecules, would suffice, as long as they carried the genetic information necessary to eventually evolve into more sophisticated forms of life. Crick and Orgel weren't proposing that aliens directly created humans or any other complex organisms. Instead, they suggested that extraterrestrial intelligence had planted the seeds from which all terrestrial life eventually grew. The subsequent evolution of plants, animals, and humans could have proceeded entirely through natural selection, but operating on genetic raw material that had been carefully crafted elsewhere. Their hypothesis also offered new perspectives on the search for extraterrestrial intelligence. If directed panspermia was correct, then SETI researchers shouldn't just be looking for radio signals from space. They should be looking for evidence of past visitations, biological signatures that might point to our cosmic parentage. The implications were profound. If life on Earth had extraterrestrial origins, then the universe might be filled with worlds sharing our basic biochemistry, making communication and even contact far more likely. We might not be alone in the cosmos, but part of a vast family of worlds, all sharing common ancestors among the stars. Crick's proposal also suggested that intelligence itself might be a cosmic phenomenon, not a rare accident. If advanced civilizations routinely seeded worlds with life, then the universe might be filled with intelligence at every stage of development. Young civilizations like ours, just beginning to explore space, mature civilizations engaged in cosmic gardening, and ancient civilizations whose biological legacy stretched across the galaxy. The scientific establishment's response to Crick's directed panspermia was more respectful than it had been to earlier panspermia proposals, but still deeply skeptical. Critics pointed out that the hypothesis was essentially untestable. How could we prove that life had been deliberately planted rather than naturally evolved? But Crick had raised questions that wouldn't go away. The phosphorus problem remained unsolved. The universality of the genetic code still seemed suspicious. The rapid appearance of sophisticated life on early Earth continued to puzzle researchers. And as our understanding of astrobiology advanced, directed panspermia began to seem less like science fiction and more like a legitimate scientific hypothesis. Today, Crick's ideas influence everything from SETI research strategies to the search for biosignatures on exoplanets. He had shown that the question of life's origins couldn't be separated from the question of intelligence in the universe, and that our own existence might be evidence that we're not the first intelligent species the cosmos has produced. In the late 1970s, something extraordinary happened in the deep ocean that would revolutionize our understanding of life's possibilities. When scientists first descended in submersibles to explore the deepest parts of our planet's seafloor, they expected to find barren landscapes, places too dark, too cold, and too toxic for life to exist. Instead, they discovered thriving ecosystems around volcanic vents, where the water reached temperatures that would instantly kill most surface life, where toxic chemicals poured from the Earth's interior, and where the pressure would crush any surface-dwelling creature in seconds. These discoveries marked the beginning of the extreme life revolution, a complete transformation in how we think about the conditions that can support living organisms. What scientists found in those crushing depths wasn't just life surviving in hostile conditions, it was life thriving in those conditions, using the very toxins and extreme temperatures that would kill surface organisms as sources of energy and building materials. The organisms they discovered became known as extremophiles, literally lovers of extremes. There were thermophiles that lived in water hot enough to cook an egg, psychrophiles that remained active in temperatures far below freezing, acidophiles that thrived in acid strong enough to dissolve metal, and barophiles that required crushing pressure to survive. Most remarkably, these weren't struggling organisms barely clinging to life. They were robust, successful species that had evolved sophisticated biochemistry perfectly adapted to their extreme environments. But the real revelation came when researchers began to understand just how extreme these organisms could be. They found bacteria living in the cooling water of nuclear reactors, using radiation as an energy source. They discovered microbes in the driest places on Earth, surviving on trace amounts of moisture and dormant for decades at a time. They found life kilometers underground, in rocks so deep and hot that no one had imagined they could harbor living things. Most startling of all were the tardigrades, microscopic creatures that became known as the ultimate survivors. These tiny animals, barely visible to the naked eye, could survive being completely dried out for years, frozen to temperatures approaching absolute zero, exposed to radiation levels thousands of times higher than what would kill humans, and even the vacuum of space itself. When European Space Agency researchers attached tardigrades to the outside of satellites and exposed them to the harsh environment of space, vacuum, radiation, extreme temperature swings, no air, no water, no food. The tardigrades not only survived but remained capable of reproduction when brought back to Earth. They had proven that complex life, not just simple bacteria, could survive in space. These discoveries fundamentally changed the panspermia hypothesis. Earlier versions had required special conditions, protected environments, or short journey times for life to survive travel between worlds. But extremophiles showed that life was far more resilient than anyone had imagined. If organisms could thrive around nuclear reactors and survive in space, then perhaps the journey between worlds wasn't the lethal gauntlet scientists had assumed. The implications extended far beyond Earth. If life could exist in such extreme conditions here, then the habitable zone around stars, the narrow band where liquid water could exist, was far too conservative. Life might exist in the subsurface oceans of frozen moons, in the acid clouds of Venus-like planets, even in the cold vacuum of space itself. Researchers began to study extremophiles as models for what life might be like on other worlds. The sulfur-metabolizing bacteria found around deep-sea vents could thrive on planets with volcanic activity and toxic atmospheres. The radiation-resistant organisms found in nuclear facilities could survive on worlds with thin atmospheres that provided little protection from cosmic rays. The pressure-loving bacteria found in deep ocean trenches could exist in the subsurface oceans of icy moons. But perhaps most important for panspermia, extremophiles showed that life had evolved not just tolerance for extreme conditions, but active strategies for surviving them. Cryptobiosis allowed organisms to essentially stop their biological clocks, entering states of suspended animation that could last for geological time periods. Radiation resistance involved sophisticated DNA repair mechanisms that could fix damage faster than it accumulated. Desiccation resistance included the production of protective compounds that preserved cellular structures even when all water was removed. These weren't just survival mechanisms, they were survival technologies, sophisticated biological systems that seemed almost designed for interplanetary travel. An organism that could survive in cryptobiosis for thousands of years, repair radiation damage, and remain viable without water was essentially equipped for space travel. The extremophile revolution also revealed that Earth's subsurface harbored a deep biosphere, an entire ecosystem of organisms living kilometers below the surface, using chemical energy instead of sunlight, and potentially representing more biomass than all surface life combined. This deep biosphere could serve as a protected reservoir of life, capable of surviving even catastrophic surface events like asteroid impacts or volcanic eruptions. If Earth had such a deep biosphere, then other worlds might too. Mars, with its evidence of past and present subsurface water, could harbour extensive underground ecosystems. The moons of the outer solar system, with their subsurface oceans, could support vast communities of extremophile organisms. Even worlds that appeared completely barren on the surface might teem with life in their hidden depths. The discovery of extremophiles also suggested that life might be far more common in the universe than previously thought. If organisms could thrive in such a wide range of conditions, then habitable environments might exist almost everywhere. In the clouds of gas giant planets, in the mantles of rocky worlds, in the ice shells of frozen moons, even in the void between stars. Most provocatively, extremophiles raised the possibility that Earth itself had been seeded by space-traveling organisms. The rapid appearance of sophisticated life forms in Earth's earliest history, the universal use of the same basic biochemistry by all terrestrial life, and the existence of organisms that seemed over-engineered for Earth's conditions all made more sense if life had originated elsewhere and arrived here, already equipped with survival technologies perfected in the harsh environment of space. The extreme life revolution had transformed panspermia from speculation into serious scientific hypothesis, supported by living proof that organisms could survive the journey between worlds and thrive in environments that mimicked the conditions they would encounter during interplanetary travel. The story of how life might travel between worlds begins with violence, the catastrophic impacts that can blast rocks from planetary surfaces and send them flying across the solar system at speeds that would make our fastest spacecraft seem like leisurely strolls through the cosmos. When an asteroid or comet strikes a planet with sufficient force, it doesn't just create a crater. The impact unleashes energies comparable to thousands of nuclear weapons, instantly vaporizing the impactor and excavating vast quantities of surface material. Most of this material falls back to the planet within hours or days, but some of it, the material closest to the impact site that receives the most energy, can be accelerated to velocities that exceed the planet's escape velocity. This isn't theoretical speculation. We have physical evidence sitting in our laboratories right now. The Allen Hills 84001 meteorite, discovered in Antarctica in the 1980s, is a piece of Mars that was blasted from the red planet's surface around 16 million years ago and eventually fell to Earth. Chemical analysis shows it definitely formed on Mars. Its composition matches what we've measured from Martian orbit and surface missions, and it contains traces of the Martian atmosphere trapped in tiny bubbles within the rock. But Allen Hills 84001 isn't alone. We've now identified dozens of meteorites that originated on Mars and several that came from the Moon. The cosmic billiards game that sends rocks flying between worlds isn't a rare occurrence, but a regular feature of solar system dynamics that has been operating for billions of years. The physics of impact ejection reveals why life might be able to survive such seemingly destructive events. When an impact occurs, the material that gets ejected comes from a zone called the spall zone, the region just outside the main impact crater where the shock waves converge and create conditions that can accelerate rocks to escape velocity without completely destroying them. While the immediate impact site is subjected to temperatures and pressures that would vaporize any organic material, rocks from the spall zone can be ejected relatively intact. Computer simulations of major impacts show that organisms buried even a few meters below the surface could survive ejection from their home planet. The acceleration happens quickly enough that the organisms experience extreme forces for only brief periods, and the rocks that protect them remain intact throughout the process. It's violent, but not necessarily lethal, more like being shot from a cosmic cannon than being incinerated in an explosion. The journey times between worlds make survival even more plausible. While some ejected rocks take millions or even billions of years to travel between planets, others follow much faster trajectories. The fastest Mars-to-Earth transfers can happen in less than a year, while typical journey times are measured in thousands rather than millions of years. These timescales are well within the survival limits of extremophile organisms in cryptobiotic states. Earth and Mars are particularly good candidates for biological exchange because their orbits bring them relatively close together on a regular basis, and because Mars's lower gravity makes it easier to eject material from its surface. Computer models suggest that Earth has received thousands of Martian rocks over geological time, with the rate of delivery being highest during periods of intense bombardment in the early solar system. But the cosmic billiards game extends beyond just the Earth-Mars system. Jupiter's large moons regularly exchange material with each other and occasionally send rocks into the inner solar system. Venus, despite its hellish surface conditions today, could have exchanged material with Earth during the early period when both planets may have had more similar environments. Even more remarkably, some ejected rocks can escape the solar system entirely, potentially carrying life to other star systems. While these interstellar journeys would take millions of years, they're not impossible. And if our solar system can export life to other stars, then other star systems could be exporting life to us. The discovery of interstellar objects like Oumuamua, the strange elongated visitor that passed through our solar system in 2017, shows that material does travel between star systems. While Oumuamua appeared to be too dry and irradiated to harbour life, it proved that interstellar panspermia is at least mechanically possible. Recent research has revealed that impact ejection can be even gentler than previously thought. Some rocks are ejected not by direct impact, but by the secondary effects of seismic waves that travel through the planet after a major impact. This seismic ejection can launch rocks into space with accelerations low enough that even delicate organisms might survive the process. The cosmic billiards game has been operating for the entire history of the solar system, but it was most active during the late heavy bombardment period around 3.8 billion years ago, when the inner solar system was subjected to intense asteroid and comet impacts. This period coincides roughly with the earliest evidence of life on Earth, suggesting that biological exchange between worlds might have been at its peak, just when life was becoming established. Perhaps most intriguingly, the impact ejection process is inherently selective. Rocks from deeper in the planet's crust, where subsurface organisms might have been protected from surface sterilization events, are more likely to be ejected intact. Organisms from stable, long-term subsurface environments, exactly the kinds of extremophiles that would be best adapted for space travel, are the ones most likely to become cosmic passengers. The violence that sends rocks flying between worlds is the same violence that could drive evolution on multiple planets simultaneously. Impacts that sterilize planetary surfaces also provide opportunities for new organisms to arrive from elsewhere, potentially accelerating evolutionary change and increasing biological diversity across the solar system. The cosmic billiards game reveals that planetary systems aren't isolated biological islands, but interconnected ecosystems where life can move freely between worlds. Every major impact is both an ending and a beginning, the end of existing ecosystems and the beginning of new possibilities as cosmic seeds take root in alien soil. Space, we're often told, is hostile to life, a vast emptiness where the vacuum would instantly boil your blood, where radiation would fry your DNA, where the cold would freeze you solid in seconds. But this perspective, shaped by our experience as large, complex, warm-blooded creatures, tells only part of the story. For microscopic life, especially organisms that have evolved sophisticated survival mechanisms, the vacuum of space can actually provide a surprisingly gentle environment for long-term survival. The vacuum itself, paradoxically, offers some of the best preservation conditions imaginable. Without air molecules to carry heat, without water to enable chemical reactions, without atmospheric pressure to stress cellular structures, organisms in space exist in a state of nearly perfect suspended animation. It's like the ultimate deep freeze, but without the ice crystals that can damage cellular structures. When researchers first exposed bacterial spores to space vacuum, they expected rapid death. Instead, they found that many organisms could survive for months or even years in conditions that would instantly kill complex life. The spores simply shut down their metabolism, entered cryptobiosis, and waited. No chemical reactions, no aging, no decay, just existence in a state of biological time suspension that could theoretically last for geological ages. The radiation environment of space presents more complex challenges, but even here, nature has evolved sophisticated solutions. Cosmic rays and solar radiation can certainly damage DNA, but many organisms have developed repair mechanisms that can fix this damage faster than it accumulates. Some bacteria can survive radiation levels thousands of times higher than what would be lethal to humans, treating cosmic rays as just another environmental factor to be managed rather than feared. More surprisingly, radiation can sometimes actually help organisms survive in space. Dense radiation fields create what scientists call radiation pressure. The physical force exerted by light and other electromagnetic radiation. This pressure can actually accelerate lightweight organisms to significant speeds, potentially helping them travel between star systems. The same radiation that threatens to damage their DNA also provides the motive power for their cosmic journeys. The temperature extremes of space, from hundreds of degrees above freezing in direct sunlight to hundreds of degrees below freezing in shadow, sound lethal, but many organisms already deal with similar conditions on Earth. Extremophiles routinely survive in environments ranging from boiling hot springs to permanently frozen Antarctic valleys. For organisms already adapted to temperature extremes, space offers nothing fundamentally new. What's more, the vacuum of space provides natural protection against one of the biggest killers of organisms on Earth: chemical contamination. There are no toxic gases in space, no acid rain, no pollutants. The environment is chemically pristine, free from the biological warfare of competing organisms that characterizes terrestrial ecosystems. For an organism in cryptobiosis, space is perhaps the cleanest environment in the known universe. The discovery that organic compounds can survive and even form in space has revolutionized our understanding of the cosmic environment. Amino acids, the building blocks of proteins, have been found in meteorites and observed forming in laboratory simulations of interstellar conditions. Complex organic molecules exist throughout the galaxy, suggesting that the ingredients of life are constantly being synthesized in the cosmic environment. Some research suggests that space conditions might actually be better for prebiotic chemistry than planetary surfaces. The low temperatures and low densities of interstellar clouds allow complex molecules to form and survive that would quickly decompose in the warmer, more chaotic environments of planetary atmospheres. Space might not just preserve life, but actively contribute to its chemical evolution. The Panspermia missions conducted by various space agencies have provided direct evidence of biological survival in space. Bacteria, fungal spores, and even small animals have been exposed to the space environment for months at a time and returned to Earth viable and capable of reproduction. These weren't specially designed, space-adapted organisms, but ordinary terrestrial life forms that turned out to be far more resilient than expected. Perhaps most remarkably, some organisms seem to actually benefit from space exposure. Certain bacterial strains show enhanced resistance to radiation and other stressors after being exposed to space conditions, as if the cosmic environment triggered adaptive mechanisms that made them more robust than their Earth-bound cousins. The timescales for survival in space are measured not in hours or days, but in millions or even billions of years. Computer models suggest that organisms protected within meteorites could remain viable for cosmic ages, surviving journeys not just between planets, but between star systems. The vacuum that seems so hostile to complex life provides almost perfect preservation conditions for microscopic organisms. The protective power of even small amounts of material is extraordinary. Just a few centimeters of rock can shield organisms from most harmful radiation while providing thermal insulation against temperature extremes. Inside meteorites, organisms exist in protected microenvironments that remain stable for millions of years, emerging unharmed when their rocky spacecraft finally reaches a destination. Recent research has revealed that space isn't truly empty, but filled with a thin but persistent medium of gas, dust, and organic compounds. This interstellar medium can provide trace amounts of chemical nutrients and even water molecules, potentially supporting minimal biological activity during long cosmic journeys. Organisms in space might not just survive, but actually grow and evolve during their travels. The gentle nature of space for microscopic life extends even to the mechanical stresses of cosmic travel. While acceleration during planetary ejection can be extreme, the subsequent journey through space is remarkably smooth. No turbulence, no vibration, no mechanical stress, just a gentle glide through the cosmic void that could last for millions of years without disturbing even the most delicate cellular structures. As we've learned more about extremophiles and their survival mechanisms, space has begun to look less like a hostile environment and more like an alternative habitat, a place where life can exist in suspension, traveling between worlds, waiting for the right conditions to resume active growth and reproduction. The vacuum of space, rather than being life's enemy, might actually be one of its most reliable allies in the quest to colonize the cosmos. The cosmos is a vast chemical laboratory, and it has been conducting experiments in organic chemistry for billions of years longer than life has existed on Earth. As we peer deeper into space with increasingly sophisticated instruments, we're discovering that the universe isn't just filled with hydrogen and helium, but with a rich tapestry of complex organic molecules, the very building blocks from which life is constructed. In the cold depths of interstellar space, where temperatures hover just a few degrees above absolute zero, vast molecular clouds stretch across light years of emptiness. These regions might seem utterly sterile, but they're actually teeming with chemical activity. Starlight and cosmic rays provide the energy for chemical reactions that would be impossible under earthly conditions, while the extreme cold preserves complex molecules that would quickly decompose in warmer environments. Spectroscopic analysis of these interstellar clouds reveals an astonishing diversity of organic compounds. Simple molecules like water, ammonia, and methane are common, but researchers have also detected amino acids, sugars, alcohols, and even complex polymers that resemble the precursors to DNA and RNA. More than 200 different molecular species have been identified in interstellar space, and new ones are discovered regularly. The formation of these organic compounds follows pathways that seem almost designed to create the building blocks of life. Cosmic rays break apart simple molecules, creating reactive fragments that can recombine in novel ways. Ice grains provide surfaces where molecules can meet and react, while ultraviolet radiation from nearby stars provides the energy to drive increasingly complex chemical reactions. Perhaps most remarkably, many of the organic compounds found in space are the same ones that appear in terrestrial biology. Glycine, the simplest amino acid and a crucial component of proteins, has been detected in comets, meteorites, and interstellar clouds. Formaldehyde and hydrogen cyanide, which can combine to form sugars and amino acids, are among the most common organic molecules in the galaxy. The famous Miller-Urey experiment of the 1950s showed that organic compounds could form under primitive Earth conditions, but subsequent research has revealed that space itself provides even better conditions for prebiotic chemistry. The low temperatures and low pressures of interstellar clouds allow complex molecules to form and survive that would quickly decompose in planetary atmospheres. Comets, those ancient wanderers from the outer reaches of the solar system, serve as time capsules preserving the organic chemistry of space. When space missions have analyzed comet tails and surfaces, they found a treasure trove of organic compounds, amino acids, complex hydrocarbons, even molecules that could serve as precursors to cell membranes and genetic material. The Rosetta mission to Comet 67P revealed that comets contain not just the building blocks of life but potentially life itself. The organic compounds detected weren't just simple molecules, but complex polymers organized in ways that suggested biological activity. While the interpretation of this data remains controversial, it opened the possibility that comets might be carriers of living systems rather than just organic chemistry. Meteorites provide another window into cosmic chemistry. The Murchison meteorite, which fell in Australia in 1969, has yielded more than 80 different amino acids, far more than the 20 used by terrestrial life. Some of these amino acids show the kind of molecular asymmetry characteristic of biological systems, suggesting they might have been processed by living organisms before their arrival on Earth. More recent meteorite studies have found evidence of even more complex organic chemistry. Nucleobases, the molecular units that make up DNA and RNA, have been detected in meteorites, along with phosphorus-containing compounds essential for energy storage and genetic information transfer. It's becoming clear that meteorites aren't just rocks from space, but repositories of cosmic biochemistry. The chemistry of space also explains some puzzling aspects of terrestrial biochemistry. Why does life use only 20 amino acids when over 80 have been found in meteorites? Why is the genetic code universal among all terrestrial life? Why do organisms use the same basic biochemical pathways, regardless of their evolutionary history? If life on Earth descended from cosmic ancestors, these questions have elegant answers. The 20 amino acids used by terrestrial biology might be the ones that were most abundant in the cosmic environment where life first evolved. The universal genetic code might reflect the biochemistry of the original cosmic organisms. The shared metabolic pathways might be inheritance from ancient space-dwelling ancestors. The discovery of organic chemistry in space has also revealed that the universe might be engaged in a form of chemical evolution, with increasingly complex molecules forming over cosmic time. Simple compounds form first, then react to create more complex ones, which in turn serve as building blocks for even more sophisticated chemistry. It's a cosmic progression from atoms to molecules to the complex chemistry of life itself. Recent research suggests that this chemical evolution might be accelerated by the extreme conditions of space. Radiation, which is often thought of as destructive, can actually drive chemical reactions that create new organic compounds. The vacuum of space prevents the reverse reactions that would break down complex molecules. The cold preserves delicate chemical structures that would be unstable at higher temperatures. Perhaps most intriguingly, some researchers propose that space itself might be capable of supporting primitive forms of life, not complex organisms like those on Earth, but simple self-replicating chemical systems that could evolve and adapt over cosmic timescales. These plasma-based life forms would exist in the ionized gas found throughout the galaxy, using electromagnetic forces instead of chemical bonds to maintain their structure. The implications are profound. If space is filled with organic chemistry, and if this chemistry can evolve toward increasing complexity, then life might not be a rare accident, but an inevitable outcome of cosmic chemical evolution. The universe might not just contain life, but be actively engaged in creating it, using the vast scales of space and time to conduct chemical experiments that no earthly laboratory could match. This cosmic chemistry also suggests that the boundaries between life and non-life might be less clear than we imagine. If organic compounds can evolve toward increasing complexity in the cosmic environment, then there might be a continuous spectrum from simple chemistry through prebiotic systems to full-fledged life, with space serving as the nursery where this progression unfolds. In the outer reaches of our solar system, beyond the orbit of Neptune, in a region so cold and dark that water exists only as ice harder than granite, drift the most ancient objects in our cosmic neighborhood. Comets, those spectacular visitors that periodically sweep through the inner solar system, trailing magnificent tails of gas and dust, are time capsules from the solar system's birth. And they may be something even more remarkable, arcs carrying life between the stars. Comets formed in the earliest days of the solar system, when the disk of gas and dust surrounding the young sun was condensing into planets and smaller bodies. Unlike the rocky planets that formed in the warm inner regions, comets condensed in the cold outer regions, where water, ammonia, methane, and carbon dioxide could freeze into solid ice. They're essentially dirty snowballs, but their dirt includes a rich mixture of organic compounds that makes them mobile chemical laboratories. The structure of a comet is perfectly designed for preserving delicate materials over cosmic timescales. The nucleus is a mixture of ice and rock, typically a few kilometers across, that remains frozen solid during the long periods when the comet is far from any star. This frozen state provides ideal preservation conditions: no chemical reactions, no decay, no aging. Any organic compounds or even living organisms trapped within the comet's ice would remain in a state of perfect, suspended animation. When a comet's orbit brings it close to the sun, the outer layers begin to sublimate, transforming directly from ice to gas without melting. This creates the spectacular coma and tail that make comets visible from Earth, but it also releases whatever materials have been preserved in the ice. If comets carry life, this is when they would deliver their precious cargo to any planets they encounter. The late heavy bombardment period, around 3.8 billion years ago, saw an intense rain of comets and asteroids throughout the inner solar system. Earth was struck thousands of times by objects large enough to vaporize entire oceans, yet somehow, life managed to establish itself during or shortly after this period of cosmic violence. Comets may have been delivering not just the water that filled our oceans, but the life that would eventually populate them. Modern space missions have revealed that comets are far more complex than simple balls of dirty ice. The European Space Agency's Giotto mission to Halley's Comet found organic compounds that were startlingly similar to those found in living systems. The more recent Rosetta mission to Comet 67P detected amino acids, complex hydrocarbons, and even molecular structures that suggested organized, possibly biological chemistry. Most remarkably, Rosetta found that the organic compounds in 67P weren't randomly distributed, but showed patterns of organization that suggested they might have been processed by biological systems. While this interpretation remains controversial, it raised the tantalizing possibility that comets might not just carry the building blocks of life, but life itself. The chemistry of comet formation supports the idea that they could serve as biological time capsules. As comets condensed in the outer solar system, they would have incorporated whatever organic materials were present in the surrounding space, including any microorganisms that might have been drifting in the interstellar medium. Once frozen into the comet's nucleus, these materials would remain perfectly preserved for billions of years. Comets also provide ideal conditions for what researchers call prebiotic chemistry, the chemical reactions that could lead from simple organic compounds to the complex molecules necessary for life. The radiation environment around comets creates the energy needed to drive chemical reactions, while the cold temperatures prevent the decomposition of delicate organic molecules. It's possible that comets serve as cosmic laboratories, where the chemistry of life continues to evolve during their long journeys through space. The orbital dynamics of comets make them excellent vehicles for distributing life throughout the solar system and beyond. Most comets follow highly elliptical orbits that take them from the outer reaches of the solar system to close encounters with the inner planets. During these passages, they could pick up materials from one world and deposit them on another, serving as biological shuttles between planets. Some comets escape the solar system entirely, carrying whatever materials they contain into interstellar space, where they could eventually encounter other planetary systems. Computer simulations suggest that our solar system loses hundreds of comets to interstellar space each year, while gaining a smaller number of interstellar visitors, like Oumuamua. This cosmic exchange could distribute life throughout the galaxy over billions of years. The discovery of organic compounds in comet tails has revealed that these ancient visitors continue to synthesize complex chemistry even as they travel through space. Spectroscopic analysis of comet emissions shows molecules forming and breaking apart in real time, driven by solar radiation and cosmic rays. Comets aren't just passive carriers of ancient chemistry, but active participants in cosmic chemical evolution. Recent research has suggested that comets might have played a crucial role in delivering not just life to Earth, but the specific chemical conditions that allowed terrestrial life to flourish. Comets carry a unique mixture of water, organic compounds, and trace elements that closely matches what would have been needed to support early life. They might have provided not just the seeds of life, but the garden in which those seeds could grow. The periodic return of comets to the inner solar system means that the delivery of cosmic materials to Earth isn't just an ancient phenomenon, but an ongoing process. Every time a comet passes close to our planet, it potentially deposits microscopic amounts of organic material and possibly even living organisms. We might be receiving regular deliveries from cosmic gardens maintained in the cold storage of the outer solar system. Perhaps most intriguingly, the study of comets has revealed that they preserve not just the chemistry of our own solar system, but potentially the chemistry of interstellar space. As they formed, comets incorporated materials from the interstellar medium, creating a record of cosmic chemistry that extends far beyond our local environment. When we study comet chemistry, we're studying the chemical heritage of the entire galaxy. The image of comets as cosmic arcs carrying life between the stars transforms our understanding of these spectacular visitors. They're not just beautiful astronomical phenomena, but potentially crucial participants in the greatest story ever told, the story of how life spreads throughout the cosmos, traveling between worlds on vessels of ice and rock that serve as libraries, laboratories, and lifeboats for the most precious cargo in the universe. Of all the worlds in our solar system, Mars holds the most tantalizing clues about life's cosmic journey. This rusty, cold world that now seems so alien was once Earth's twin, warm, wet, and possibly teeming with life. As we've explored Mars with increasingly sophisticated robots and analyzed Martian meteorites in our laboratories, a compelling picture has emerged. Mars may not just have harbored life, but may have been life's launching pad for a cosmic journey that eventually led to Earth. The story begins 4 billion years ago, when Mars was a very different world. The planet had a thick atmosphere, flowing rivers, vast lakes, and possibly even oceans. The climate was warm enough for liquid water to exist on the surface for hundreds of millions of years, far longer than it took for life to establish itself on Earth. If life could emerge on ancient Earth, it almost certainly could have emerged on ancient Mars as well. But Mars had advantages that early Earth lacked. The planet's lower gravity made it easier for rocks to be ejected into space by asteroid impacts. Its thinner atmosphere provided less protection from cosmic radiation, which might have actually helped drive the chemical evolution that leads to life. Most importantly, Mars may have become habitable earlier than Earth, giving Martian life a head start of hundreds of millions of years. The Allen Hills 84001 meteorite, that famous piece of Mars that fell to Antarctica, provided the first tantalizing hint that life might have made the journey from Mars to Earth. When researchers examined the meteorite in the 1990s, they found structures that looked remarkably like fossilized bacteria, tiny, worm-like features embedded in the rock that were organized in ways that seemed biological. The interpretation of these structures remains controversial, but subsequent analysis has revealed that Allen Hills 84001 contains organic compounds that could only have formed in the presence of water and possibly life. The meteorite shows evidence of having been in contact with liquid water on Mars for extended periods, exactly the conditions where life might have thrived. More recently, NASA's Mars rovers have been uncovering evidence that ancient Mars was even more habitable than we imagined. The Curiosity and Perseverance rovers have found complex organic compounds in Martian rocks, evidence of ancient rivers and lakes that persisted for millions of years, and mineral deposits that form only in the presence of liquid water. Most remarkably, they've detected methane in the Martian atmosphere, a gas that on Earth is primarily produced by living organisms. The methane detections are particularly intriguing because methane breaks down quickly in the Martian atmosphere. For it to be present in measurable quantities, it must be continuously replenished by some active source. While geological processes could potentially produce methane, biological processes are far more likely. The seasonal variations in methane levels, with concentrations rising during the Martian spring and summer, suggest the kind of cyclical activity we might expect from living organisms. But perhaps the strongest evidence for a Martian origin of life comes from the timing of events in the early solar system. Life appears in the geological record on Earth almost as soon as conditions became favourable, around 3.8 billion years ago. This rapid appearance is puzzling if life had to evolve from scratch on Earth, but it makes perfect sense if life had already evolved elsewhere and was simply waiting for suitable conditions to establish itself. Mars became habitable several hundred million years before Earth, giving Martian life ample time to evolve and spread throughout the planet's subsurface. When the late heavy bombardment began pummeling the inner solar system with asteroids and comets, Mars would have been exporting billions of rocks to Earth, Venus, and other worlds. If any of those rocks contained Martian microorganisms, they could have seeded life throughout the inner solar system. The subsurface of Mars remains potentially habitable today. Liquid water exists in underground aquifers, protected from the harsh surface conditions by kilometers of rock. The temperature and pressure in these subsurface environments are similar to conditions in Earth's deep biosphere, where organisms thrive using chemical energy instead of sunlight. If life originated in Mars's subsurface, it could still be there, quietly continuing the evolutionary journey that began billions of years ago. Recent discoveries have revealed that the exchange of material between Mars and Earth has been far more extensive than previously thought. Computer simulations suggest that Earth has received thousands of Martian meteorites over geological time, with the rate of exchange being highest during the period when life was first establishing itself on both worlds. The two planets have been in constant biological communication for billions of years. The implications extend beyond just the origin of terrestrial life. If Mars was indeed the source of Earth's biology, then the two worlds share a common evolutionary heritage. Martian life and terrestrial life would be cousins, separated by millions of years of independent evolution, but sharing the same fundamental biochemistry and genetic heritage. The search for life on Mars isn't a search for aliens, but a search for our cosmic family. This Martian connection also suggests that life might be far more resilient and widespread than we imagine. If organisms could survive the journey from Mars to Earth billions of years ago, they could have made similar journeys to other worlds throughout the solar system. Venus, Jupiter's moons, Saturn's moons, and countless other bodies could harbour descendants of ancient Martian life. The robotic exploration of Mars has entered a new phase with the Perseverance rover actively collecting samples for eventual return to Earth. These samples, carefully selected from locations that show the strongest evidence of past habitability, could finally provide definitive proof of Martian life. If they contain fossilized microorganisms or clear biosignatures, it would confirm that life did indeed originate on Mars before spreading to Earth. But even if current Mars missions don't find direct evidence of life, the planet's role as a potential launching pad for cosmic biology remains compelling. The chemical, geological, and temporal evidence all point toward Mars as a more likely birthplace for solar system life than Earth itself. In the grand story of life's cosmic journey, the red planet may not be our destination but our starting point. The Martian connection transforms our understanding of both worlds. Earth may not be a unique oasis of life in a sterile cosmos, but one node in a vast biological network that includes Mars and potentially countless other worlds. We may not be alone in the universe. We may never have been alone, because the cosmos has been alive and spreading life for far longer than we ever imagined. When we look at Venus today, we see a hellish world where lead would melt on the surface, where the atmosphere is thick enough to crush submarines, and where sulfuric acid rains from clouds of poison. It seems impossible that this infernal planet could have anything to do with life's cosmic journey. But this perspective may be our greatest astronomical mistake, a failure to see Venus not as it is, but as it once was, when it may have been the most habitable world in the solar system. 4 billion years ago, Venus was Earth's true twin. Both planets formed at roughly the same time from the same materials in the same region of the solar system. Both had similar sizes, similar masses, and similar compositions. But Venus had one crucial advantage. It received more solar energy, which meant its surface warmed more quickly, allowing liquid water to exist earlier in its history than on either Earth or Mars. Climate models of the early solar system reveal that Venus may have had liquid oceans for up to 2 billion years, far longer than the few hundred million years that Mars remained habitable. During this enormous span of time, Venus could have developed not just life, but complex ecosystems that had ample time to evolve sophisticated survival mechanisms. If life existed on ancient Venus, it would have had a billion-year head start on terrestrial biology. The transformation of Venus from a potentially habitable world to the hellscape we see today occurred through a runaway greenhouse effect that may have taken millions of years to complete. As the young sun gradually became brighter, Venus received more and more solar energy. Eventually, the planet's oceans began to evaporate, filling the atmosphere with water vapor. Water vapor is itself a greenhouse gas which trapped more heat, which evaporated more oceans, in a feedback loop that ultimately boiled away every drop of liquid water on the planet. But this catastrophic transformation may have provided the perfect opportunity for Venusian life to escape their dying world. As the planet's surface became increasingly uninhabitable, organisms that had evolved in the planet's oceans and atmosphere would have faced extinction unless they could find refuge elsewhere. The same atmospheric disruption that made Venus uninhabitable also made it easier for rocks to be ejected from the planet's surface by asteroid impacts. Computer simulations show that rocks ejected from Venus during this period could have reached both Earth and Mars, potentially carrying Venusian organisms to both worlds. The timing is particularly intriguing. Venus underwent its climate catastrophe during the same period when life was first appearing on Earth. What we've interpreted as the rapid emergence of terrestrial life could actually be the rapid colonization of Earth by Venusian refugees. This scenario would explain many puzzling aspects of early life on Earth. Why did life appear so quickly after Earth's surface cooled? Because it didn't need to evolve from scratch. It arrived already fully formed from Venus. Why did early organisms already possess sophisticated biochemical pathways? Because they had evolved over billions of years in Venusian oceans before making the journey to Earth. Most remarkably, life may still exist on Venus, not on the hellish surface, but floating in the planet's cloud layers, where temperatures and pressures are similar to those found on Earth. At altitudes of 50 to 60 kilometers above Venus's surface, the environment is surprisingly benign, warm but not hot, with plenty of water vapor and only moderate acidity. Organisms that evolved in Venus's ancient oceans might have taken refuge in these aerial ecosystems when the surface became uninhabitable. The recent detection of phosphine gas in Venus's atmosphere has electrified the astrobiology community. On Earth, phosphine is produced almost exclusively by living organisms. It's a biosignature that's difficult to explain through purely geological processes. While the phosphine detection on Venus remains controversial and requires confirmation, it raises the tantalizing possibility that the planet's cloud layers harbor active biological ecosystems. If life does exist in Venus's atmosphere, it would represent one of the most remarkable survival stories in the known universe. These organisms would be the descendants of creatures that survived the complete transformation of their world, adapting to an aerial existence as their original ocean habitat boiled away. They would have been living in Venus's clouds for over 3 billion years, possibly making them the oldest continuously existing ecosystem in the solar system. The study of Venus's atmospheric chemistry has revealed conditions that, while challenging, aren't necessarily incompatible with life. The clouds contain water vapor, carbon dioxide, sulfur dioxide, and various sulfur compounds, a mixture that some extremophile organisms on Earth can use as an energy source. The acidity, while extreme, is within the tolerance range of Earth's most acid-loving organisms. Recent research has also suggested that Venus's clouds might contain solid particles that could serve as floating habitats for airborne organisms. These particles could provide surfaces for biochemical reactions and might even form complex structures, resembling aerial islands where entire microbial ecosystems could thrive. The implications of Venusian life extend far beyond our solar system. If organisms can survive in Venus's cloud layers, then similar aerial ecosystems might exist on countless other worlds throughout the galaxy. Gas giant planets, which are far more common than rocky planets, all have atmospheric regions where temperature and pressure conditions are suitable for life. Venus might be showing us that the habitable zone around stars is far larger than we've imagined. But perhaps most importantly, Venus challenges our assumptions about what makes a world habitable. We've been looking for planets that are just like Earth, not too hot, not too cold, with liquid water on the surface. But Venus suggests that habitability might be more about adaptability than about perfect conditions. Life might not need an ideal environment. It might just need an environment that it can modify to become ideal. The story of Venus is a story about resilience, adaptation, and survival against impossible odds. If life originated there and survived the planet's transformation, then it demonstrates that biology is far more flexible and persistent than we've imagined. And if Venusian life seeded other worlds during its planet's climate catastrophe, then Venus might have been the true cradle of solar system biology, the garden world that gave birth to life on Earth and Mars alike. This transforms Venus from a cautionary tale about runaway climate change into an inspirational story about life's ability to survive and spread, even in the face of planetary catastrophe. The brilliant morning star that graces our skies might not be a dead world at all, but the ancient mother of all solar system life, still harboring the descendants of the organisms that first learned to live among the clouds. Hidden within every living cell on Earth lies a molecular timekeeper that has been quietly recording the history of life for billions of years. This timekeeper, the gradual accumulation of changes in DNA and protein sequences, functions like a cosmic clock, allowing scientists to peer back through time and reconstruct when different forms of life first appeared. But this molecular clock has revealed something deeply puzzling. Life on Earth appears to be far older than the planet itself could support. The molecular clock works on a simple principle. Over time, DNA accumulates small changes, mutations that alter individual letters in the genetic code. These mutations accumulate at roughly predictable rates, allowing scientists to compare the DNA of different species and calculate how long ago they shared a common ancestor. It's like using the number of differences between related languages to estimate when they split from a common parent language. When scientists first applied molecular clock techniques to the deepest branches of the tree of life, they expected to find that the earliest organisms appeared around 3.5 billion years ago, roughly when the first fossil evidence of life appears in the geological record. Instead, they found something that seemed impossible. The molecular evidence suggested that life's most fundamental divisions occurred much earlier, perhaps as far back as 4.2 or even 4.4 billion years ago. This creates what researchers call the molecular clock problem. 4 billion years ago, Earth was still in the final stages of its formation, subjected to massive asteroid impacts that would have repeatedly sterilized the surface and vaporized any oceans. The conditions were so hostile that many scientists believed life couldn't have survived, let alone evolved, into the complex biochemical systems indicated by molecular evidence. But the molecular clock problem becomes far less problematic if we consider that life didn't necessarily originate on Earth. If terrestrial life descended from cosmic ancestors that had already undergone billions of years of evolution elsewhere, then the molecular evidence makes perfect sense. The ancient divergences recorded in our DNA might reflect evolutionary events that occurred not on early Earth, but in more hospitable environments elsewhere in the cosmos. The ribosome, the cellular machinery that translates genetic information into proteins, provides some of the most compelling molecular evidence for life's ancient origins. Ribosomal RNA sequences are among the most conserved in all of biology, changing so slowly that they preserve information about the very earliest stages of life's evolution. When scientists analyze these sequences, they find evidence of evolutionary sophistication that seems to require more time than Earth's early history could provide. The universal genetic code presents another puzzle. All life on Earth uses the same basic system for translating DNA into proteins, The same 20 amino acids, the same 3-letter codons, the same start and stop signals. This universality is remarkable because there are millions of possible genetic codes that could work equally well. The fact that all terrestrial life uses exactly the same code suggests they all descended from a single common ancestor. But molecular analysis of this genetic code reveals that it's not just universal, it's nearly optimal. Computer simulations show that the standard genetic code is more resistant to the harmful effects of mutations than almost any other possible code. This suggests that the code wasn't shaped by random chance, but by billions of years of evolutionary refinement. Such optimization would require enormous spans of time, more time than early Earth could have provided. The molecular clock also reveals puzzling patterns in the timing of major evolutionary innovations. Photosynthesis, the process that converts sunlight into chemical energy, appears to have evolved remarkably early in Earth's history, perhaps as early as 3.8 billion years ago. But photosynthesis is extraordinarily complex, involving dozens of precisely coordinated proteins and thousands of chemical reactions. The molecular evidence suggests it would have taken billions of years to evolve such sophisticated biochemistry. If photosynthesis evolved elsewhere and arrived on Earth already fully formed, this apparent contradiction disappears. Cosmic organisms would have had ample time to perfect these complex biochemical pathways in environments where conditions remained stable for billions of years. When they arrived on Earth, they would have brought with them the accumulated biochemical wisdom of cosmic ages. The horizontal gene transfer that characterizes early evolution also makes more sense in a cosmic context. During life's earliest history on Earth, organisms regularly exchanged genetic material with each other, creating a web of shared inheritance that makes it difficult to construct traditional evolutionary trees. This genetic promiscuity is exactly what we might expect if early Earth was being colonized by multiple waves of cosmic immigrants, each bringing their own genetic innovations and sharing them with the existing biological community. Recent discoveries about Earth's deep biosphere add another layer to the molecular clock problem. Life exists kilometers beneath Earth's surface, in environments that have remained stable for millions or even billions of years. These deep organisms show molecular signatures suggesting they diverged from surface life very early in Earth's history. Again, earlier than surface conditions should have permitted complex life to exist. But if these deep organisms are descendants of cosmic colonists that took refuge in Earth's subsurface when they arrived, their ancient molecular signatures become understandable. They might represent the most direct descendants of the original space-traveling organisms, preserved in deep environments that have changed little since the early bombardment period. The molecular clock problem also appears in the evolutionary history of specific biochemical pathways. DNA replication, protein synthesis, and cellular energy production all show molecular evidence of being much older than their first appearance in the fossil record would suggest. These aren't simple biochemical processes, but sophisticated molecular machines that would have required enormous amounts of time to evolve. Perhaps most intriguingly, some molecular evidence suggests that certain aspects of terrestrial biochemistry might have been shaped by environments that don't exist on Earth. Some enzymes work optimally at temperatures or pressures that are never found in terrestrial environments, suggesting they evolved elsewhere and retained their adaptation to alien conditions even after arriving on Earth. The molecular clock that ticks within every living cell tells a story of life's cosmic antiquity, a story that makes sense only if biology is far older and more widespread than we've imagined. The DNA that defines every organism on Earth might be a genetic memory of cosmic journeys, preserving the molecular signatures of life's passage between worlds and the evolutionary history of organisms that first learned to live among the stars. As we drift deeper into the 21st century, our understanding of life's cosmic possibilities has exploded far beyond the simple question of whether we are alone. The emerging field of astrobiology has transformed from speculation into rigorous science, revealing that the universe may not just contain life, but may be structured in ways that actively promote life's emergence and spread across cosmic distances. The discovery of exoplanets, worlds orbiting distant stars, has revolutionized our perspective on cosmic habitability. When the first exoplanets were discovered in the 1990s, they were strange, hostile worlds, gas giants orbiting so close to their stars that their atmospheres were being blown away into space. But as detection techniques improved, astronomers began finding Earth-like worlds in the habitable zones of distant stars, places where liquid water could exist on planetary surfaces. Today, we know of thousands of exoplanets, and statistical analysis suggests that nearly every star in the galaxy hosts at least one world. Of these countless planets, perhaps billions exist in conditions that could support life as we know it. The universe isn't just big, it's filled with potential homes for biology, on scales that dwarf our wildest imagination. But the most exciting discoveries have come not from distant stars but from within our own solar system. Europa, Jupiter's ice-covered moon, harbours an ocean beneath its frozen surface that contains more water than all of Earth's oceans combined. This isn't just a curiosity, it's a potentially habitable world that has remained stable for billions of years, protected from cosmic radiation by its ice shell and heated by the gravitational forces of Jupiter itself. Enceladus, one of Saturn's smaller moons, has surprised scientists even more. The Cassini spacecraft discovered that this tiny world is geologically active, shooting geysers of water vapor and organic compounds into space from its south polar region. Chemical analysis of these geysers revealed conditions that could support life. Liquid water, organic compounds, and chemical energy sources that organisms could use for metabolism. Titan, Saturn's largest moon, presents a completely different model of habitability. Its thick atmosphere and lakes of liquid hydrocarbons create conditions unlike anywhere else in the solar system. While too cold for liquid water, Titan's environment could potentially support exotic forms of life based on different chemistry. Organisms that use liquid methane instead of water as their biological solvent. These discoveries have expanded the concept of habitable zones far beyond the narrow band around stars where liquid water can exist on planetary surfaces. Subsurface oceans, protected by ice shells and heated by gravitational forces, could remain habitable for billions of years, regardless of their distance from stars. This means that habitable environments might be hundreds of times more common than previously thought. The James Webb Space Telescope has opened new frontiers in the search for biosignatures, chemical signs of life that could be detected in the atmospheres of distant worlds. Oxygen, water vapor, methane, and other gases that could indicate biological activity can now be detected around planets orbiting nearby stars. Each new observation brings the possibility that we might detect clear evidence of life beyond our solar system. But perhaps the most profound implication of astrobiology's advances is what they reveal about life's cosmic connectivity. If subsurface oceans exist throughout the outer solar system, and if these environments can remain habitable for billions of years, then life that originated in one location could potentially spread to countless other worlds through panspermia processes. The discovery of extremophiles on Earth has shown that life can survive in environments that closely resemble those found throughout the cosmos. Organisms that thrive in the radiation-rich environments around nuclear reactors could survive on worlds with thin atmospheres. Bacteria that live in highly acidic conditions could thrive in the subsurface oceans of icy moons. Life forms that flourish in the high-pressure depths of Earth's oceans could exist in the vast subsurface seas of distant worlds. Recent research has revealed that organic chemistry is ubiquitous throughout the universe. The same complex molecules that serve as the building blocks of life on Earth have been detected in interstellar clouds, around other stars, and even in galaxies billions of light years away. The universe appears to be naturally generating the chemical precursors of biology on cosmic scales. The concept of panspermia has evolved from speculative hypothesis to testable scientific theory. Future space missions will carry increasingly sophisticated instruments capable of detecting trace amounts of organic material or even living organisms in samples from Mars, Europa, Enceladus, and other potentially habitable worlds. If life is found in multiple locations within our solar system, and if that life shares common biochemical features, it would provide strong evidence for biological exchange between worlds. Breakthrough propulsion technologies are making interstellar panspermia seem increasingly plausible. While we're still decades away from sending spacecraft to other star systems, we're beginning to understand how such journeys might be accomplished. If human technology can eventually enable interstellar travel, then much more advanced civilizations could have been seeding life throughout the galaxy for millions or billions of years. The search for extraterrestrial intelligence has also been transformed by astrobiological discoveries. Instead of just listening for radio signals, SETI researchers now consider the possibility that evidence of extraterrestrial intelligence might be found in the form of biological signatures, signs that life on Earth or other worlds has been deliberately modified or enhanced by cosmic gardeners. Perhaps most importantly, astrobiology has revealed that the question isn't whether life exists elsewhere in the universe, but how common it is and how it spreads between worlds. The cosmic environment appears to be not just compatible with life, but actively supportive of biological processes. From the organic chemistry of interstellar space to the vast subsurface oceans of icy moons, the universe seems structured to promote life's emergence and distribution. This new understanding transforms our perspective on humanity's place in the cosmos. We may not be alone on a small planet orbiting an ordinary star in an unremarkable galaxy. Instead, we may be participants in a vast cosmic biological system that spans the universe itself. A system in which life, intelligence, and consciousness are not rare accidents but natural outcomes of cosmic evolution. As we prepare for the next phase of space exploration, with missions to Europa, Enceladus, and Mars carrying sophisticated life detection instruments, we stand on the threshold of discoveries that could reveal the true scope of life's cosmic presence. The universe may be about to welcome us home. As your breathing slows and your consciousness settles into that gentle space between waking and sleeping, let yourself absorb the profound possibility we've explored together tonight. Every breath you take, every heartbeat, every thought that drifts through your mind might be the continuation of a story that began not in some warm little pond on ancient Earth, but among the stars themselves. If the Panspermia hypothesis is correct, then you are not merely a terrestrial being who happened to evolve on this particular planet. You are a cosmic citizen, a descendant of ancient travelers who journeyed across unimaginable distances to reach this world. The atoms in your body were forged in the hearts of dying stars, and the life that animates those atoms may have begun its journey billions of years ago in environments so alien that we can barely imagine them. This isn't just a story about biology or chemistry or physics. It's a story about connection, the deepest, most fundamental connection possible. If life originated elsewhere and spread throughout the cosmos, then every living thing on Earth, from the smallest bacterium to the largest whale, from the humblest moss to the human reading these words, shares a common heritage that stretches back to the very origins of the universe itself. Consider what this means for your place in the grand story of existence. You are not an isolated consciousness trapped on a small rock orbiting an ordinary star. You are part of a cosmic community that may span the entire universe, a vast network of living worlds, connected by the patient wanderings of life itself across the ocean of space and time. The evidence we've explored tonight suggests that this cosmic community is not just theoretical but real and active. Mars may still harbour the descendants of the organisms that seeded life on Earth. Venus's clouds may shelter aerial ecosystems that represent the oldest continuous biological communities in the solar system. The moons of Jupiter and Saturn may hide vast subsurface oceans teeming with life that shares our deepest biological heritage. And beyond our solar system, around countless other stars, worlds may exist where the same basic biochemistry that powers your thoughts and dreams has taken forms we can't yet imagine. Perhaps some of these worlds harbour intelligence that evolved from the same cosmic seeds that eventually gave rise to human consciousness. Perhaps we have cosmic cousins looking up at their own night skies, wondering if they're alone, unaware that they share ancestry with every living thing on Earth. But Panspermia offers more than just intellectual satisfaction about our cosmic connections. It fundamentally changes our responsibilities as conscious beings. If we are citizens of the cosmos rather than just residents of Earth, then our obligations extend far beyond our own planet. We become stewards not just of terrestrial life, but of a cosmic biological heritage that may be billions of years old. This cosmic perspective transforms how we think about environmental protection, space exploration, and our relationships with other forms of life. If all earthly biology shares common cosmic ancestry, then protecting biodiversity becomes not just an environmental imperative, but a cosmic one. Every species that goes extinct takes with it unique genetic information that represents millions of years of cosmic evolutionary experimentation. The panspermia hypothesis also suggests that we may have a cosmic destiny. If life spreads naturally between worlds, and if intelligence is a natural outcome of biological evolution, then perhaps conscious beings like ourselves play a role in life's cosmic dissemination. We may be approaching the point where we can deliberately seed other worlds with life, continuing the cosmic gardening that may have given rise to our own existence. Our space exploration efforts take on new meaning in this context. When we send rovers to Mars, probes to the outer moons, and eventually human explorers to other worlds, we're not just satisfying scientific curiosity. We may be reconnecting with our cosmic family, establishing contact with biological communities that share our deepest heritage, or even taking the first steps toward continuing life's cosmic journey to new worlds around distant stars. The search for extraterrestrial life becomes not a search for the alien, but a search for the familiar, for life that shares our basic biochemistry because it shares our cosmic origins. When we eventually detect signs of life elsewhere in the universe, whether in the subsurface oceans of icy moons or the atmospheres of distant exoplanets, we may be discovering not strangers but relatives. This transforms the ancient question of whether we are alone in the universe. If panspermia is correct, then we have never been alone. We have always been part of a vast cosmic community, connected to life throughout the universe by bonds deeper than any earthly relationship. The loneliness that sometimes strikes us when we contemplate the vastness of space may be based on a fundamental misunderstanding of our place in the cosmos. Instead of being isolated on a tiny planet in a vast, empty universe, we may be participants in the greatest community imaginable. A community that includes every living thing that has ever existed anywhere in the cosmos, connected by the patient work of chemistry and time and the gentle persistence of life itself. As you let these ideas settle into your consciousness, notice how they change your relationship with the night sky. Those distant stars are no longer alien and unreachable. They may be the birthplaces of your most ancient ancestors. The planets orbiting those stars may harbor life that shares your deepest biological heritage. The vast spaces between the stars may be highways along which life travels, connecting world to world in an endless exchange of biological possibility. Even the air you breathe takes on new meaning. The oxygen produced by plants connects you to photosynthetic processes that may have been perfected billions of years ago in environments so distant that their light hasn't yet reached Earth. Every breath is a reminder of your participation in cosmic processes that span the universe. The panspermia hypothesis offers a new mythology for the scientific age, a story that satisfies both our need for cosmic connection and our demand for scientific rigor. It's a story in which we are neither the accidental products of random chemical reactions nor the special creations of supernatural intervention, but the natural outcomes of cosmic processes that have been operating for billions of years across the entire universe. In this story, consciousness itself takes on cosmic significance. If intelligence arises naturally from the biological processes that panspermia spreads throughout the universe, then consciousness may be not a rare accident, but a natural feature of cosmic evolution. The thoughts you think, the wonder you feel when contemplating the night sky, the very capacity for self-reflection that allows you to ponder these ideas. All of this may be the universe becoming aware of itself through billions of years of cosmic biological evolution. As you drift towards sleep, let yourself rest in this profound connectedness. You are not alone on a tiny planet in a vast, indifferent universe. You are part of the universe itself, participating in its greatest achievement, the emergence of life and consciousness from the dance of atoms and energy that began with the cosmos itself. Rest now, cosmic traveler, in the knowledge that you are part of something magnificent, a story that spans space and time, connecting every living thing in a vast web of biological relationship that makes the entire universe not just alive, but family. The stars that shine down on your dreaming are not distant and foreign, but are calling you home to a heritage deeper and older than any earthly ancestry. Sleep peacefully in your place in the cosmic community, dreaming of worlds beyond number, where life continues its eternal journey, carrying consciousness like a gentle flame through the infinite darkness, lighting the way toward futures we can barely imagine, but are destined to help create. Throughout this gentle journey into life's cosmic possibilities, we've woven together threads of evidence that suggest something profound about our place in the universe. The smooth transitions between each discovery, each piece of evidence, each philosophical implication create a tapestry that reveals not just how life might travel between worlds, but why this possibility transforms everything we thought we knew about ourselves. From the ancient wisdom of Greek philosophers to the cutting-edge discoveries of modern astrobiology, the Panspermia hypothesis has evolved from speculation into serious science. Each advancement in our understanding has added new layers of possibility, new evidence that life might indeed be a cosmic phenomenon rather than a terrestrial accident. The extremophiles that thrive in Earth's most hostile environments serve as living proof that organisms can survive conditions once thought impossible. Their existence bridges the gap between theoretical possibility and demonstrated reality, showing us that the journey between worlds is not just mechanically feasible, but biologically survivable. The chemistry we've discovered throughout the cosmos provides the raw materials from which life can emerge. From the organic compounds detected in interstellar clouds to the amino acids found in meteorites, the universe appears to be actively engaged in creating and preserving the building blocks of biology. This cosmic chemistry laboratory has been operating for billions of years, continuously synthesizing the molecules that serve as life's foundation. The transfer mechanisms we've explored, from impact ejection to comet delivery, demonstrate that material exchange between worlds is not just possible, but ongoing. Every major impact that creates destruction also creates opportunity, sending potential seeds of life across the cosmic ocean where they might take root in alien soil. The evidence from Mars, Venus, and the outer solar system reveals that habitable environments have existed throughout our cosmic neighborhood for billions of years. These worlds provided the stable conditions where life could evolve sophisticated survival mechanisms before beginning its journey to Earth. They serve as stepping stones in life's cosmic migration, waypoints in a journey that may span the entire galaxy. The molecular clocks ticking within our DNA preserve the memory of this cosmic heritage, recording evolutionary events that extend far back into cosmic time. These genetic timekeepers tell a story of biological antiquity that makes sense only if life's origins reach back far beyond Earth's early history, into cosmic environments where evolution had ample time to perfect the sophisticated biochemistry we see today. As we stand on the threshold of new discoveries, with space missions preparing to explore Europa's subsurface ocean, to analyze samples from Mars, to study the atmospheric chemistry of distant exoplanets, we approach answers to questions that have puzzled humanity since we first looked up at the stars and wondered about our place among them. But perhaps the most important aspect of the Panspermia hypothesis isn't its scientific implications, but its philosophical ones. This gentle possibility that we are cosmic citizens, rather than terrestrial accidents, changes how we see ourselves, our relationships with other life forms, and our responsibilities as conscious beings in a living universe. The loneliness that sometimes accompanies our contemplation of cosmic vastness dissolves when we realize we may never have been alone. The apparent isolation of Earth in the cosmic dark becomes an illusion when we understand that life itself may connect us to every corner of the universe. The search for extraterrestrial life transforms from a search for the alien into a search for our cosmic family. As your consciousness settles into the peaceful space between waking and sleeping, let these ideas integrate naturally into your understanding of the world. Don't force comprehension, but allow wonder to wash over you like gentle waves. The universe may be far stranger and more wonderful than we've imagined, but it's also far more connected and far more alive. Every organism you've ever encountered, every pet you've loved, every plant you've admired, every person who has touched your life may be part of an extended cosmic family that reaches back billions of years to origins among distant stars. The biological processes that sustain your life may be the continuation of processes that began in environments so alien we can barely conceive them. The Panspermia hypothesis doesn't diminish the wonder of life, but amplifies it beyond all earthly boundaries. It suggests that consciousness itself may be a cosmic phenomenon, that the thoughts you think and the emotions you feel are part of the universe's way of knowing itself. Your capacity for wonder, your ability to contemplate these vast possibilities, may itself be evidence of life's cosmic heritage. Rest in this profound connectedness as sleep approaches. You are not a temporary accident on a meaningless rock, but a cosmic expression of the universe's creativity, a continuation of processes that span space and time on scales that dwarf human comprehension. The stars that shine in the darkness are not foreign and unreachable, but are calling you home to a heritage deeper than any earthly ancestry. Let your breathing slow as you absorb these possibilities. Feel your heartbeat as a rhythm that connects you to every living thing that has ever existed anywhere in the cosmos. Allow your consciousness to expand beyond the boundaries of individual identity, to embrace your role as a participant in the greatest story ever told, the story of how the universe came alive. In your dreams tonight, you may travel across cosmic distances, visiting worlds where your most ancient ancestors first learned to live among the stars. You may see through eyes that evolved in alien oceans, think thoughts that were first thought under foreign suns, feel connections that span the galaxy itself. Sleep peacefully, knowing that you are both beautifully small and magnificently vast, a temporary expression of cosmic processes that are eternal, a fleeting moment in a story that encompasses the entire universe, a single note in a symphony that has been playing among the stars since the cosmos began. Dream deeply of your place in this vast community of consciousness, and wake tomorrow with renewed sense of wonder at the possibility that we are all, every one of us, travelers from the stars who have found our way home to this beautiful world, carrying within us the memory of cosmic journeys and the promise of cosmic futures yet to be born.